In this video, we're going to solve the Schrödinger equation for a one-electron atom. The simplest one-electron atom is the hydrogen atom. The Schrödinger equation is h hat operating on psi equals E times psi. Since we're in 3 dimensions, we'll have 3 degrees of freedom. And for the hydrogen atom, it's most convenient to use spherical coordinates, r, theta, and phi. In spherical coordinates, the Hamiltonian, which consists of a kinetic energy term and a potential energy term, is written in a long expression. The kinetic energy term contains several derivatives. It contains a term that has derivatives with respect to r. It contains a term that has theta derivatives. And last, it has a term that only has a phi derivative. The last 2 terms together, we've seen them before for the rigid rotor. Let's abbreviate them with uppercase lambda hat squared. I'm not going to spell out the potential at this time, but the Coulomb potential is given by this equation here. Z is the nuclear charge, so for hydrogen it would be 1, for helium it would be 2, and so on. Now, looking at this Hamiltonian operator, we see that there are no mixed derivatives. So we can try a separation of variables, which is a standard approach to solve these type of equations. We're going to write psi as a product of 3 functions, of a radius function, a theta function, and a phi function. We're going to collect the 2 angle dependencies into a single function, uppercase y. And our main goal will be to determine r and y. If we insert this r times y for psi into the Schrödinger equation, we get the following expression. It looks fairly complicated, but we have ry spelled out, and we can now simplify. Let's pull out r and y wherever possible from the operators and divide by y. So for the derivative with respect to r, you can pull out y, and for the derivative with respect to theta and phi, you can pull out r. Dividing by y will eliminate y everywhere, here, here, and here, and we'll put a 1 over y factor in front of the lambda squared y. Now this green term here is the only term that depends on theta and phi. Nothing else depends on phi, that just depends on r. Therefore, this must be a constant. And the equation we extract from here is this one here. Now we've seen this before for the rigid rotor. The rigid rotor equation contained the same operator. It looked like this, the Schrödinger equation for it. It had a prefactor of h bar squared over 2i in front of it. It was equal to the energy times y. The energy for the rigid rotor turned out to be h bar squared over 2i times j plus 1. Here I'm going to use L instead of j. Important note here. So we can combine this equation here and this equation here, and then obtain an equation for how to operate with lambda hat squared on y. That is equal to negative L times L plus 1. Now this is a very useful result. We can substitute it back into the above equation. And here is the result of the substitution. We get a term that contains just L times L plus 1. We've eliminated completely the angular dependence in this equation. The only thing that's unknown at this point here is the radial function r of r. And we're going to solve for this now. We're going to concentrate on bound states where the energy is smaller than 0. Non-bound states or free states have energies larger than 0. We're not going to care about those at this point. This equation has a structure that can be physically interpreted. The first term represents the radial kinetic energy. It only depends on r and does not have anything that relates to electrostatics or to centrifugal forces. Then the second term in green is the angular kinetic energy. It contains L times L plus 1, which is related to the angular momentum or to the rotation of the electron around the nucleus. The third term is a radial potential energy, and that is the Coulomb attraction. It contains nuclear charges, and it also contains 1 over r, which is the dependence. All right, let's solve it now. The first step is we're going to do some simplifications. We're going to multiply by this factor here and by r, and we'll get this expression here. Now we can introduce a bunch of abbreviations. Let's take r times r and call it u. Next, we're also going to abbreviate this prefactor here in front of the 1 over r from the Coulomb term and call it B. Lastly, let's take this prefactor here and abbreviate it with k squared. If k squared is this, then k, of course, is equal to this, the square root of negative 2me times e all over h bar. Now that negative sign might look like a problem, but it is not. Remember that the energy for bound states is negative, so a negative quantity with a negative sign in front gives a positive, and we can take the square root. So k is actually real. With these abbreviations of u, k, and b, we can rearrange the equation to look like this. It looks much simpler now. And note that now it's an equation in u, and not an equation in r anymore. Next, let's divide by 4k squared and introduce yet another abbreviation, rho. Rho is equal to 2kr and basically represents a scaled radius that is unitless. Inserting this, we'll get finally an equation of u that is a function of rho and not a function of r anymore. And now this equation is fairly easy to solve. Here is how it works. I've copied it on the top left of the slide. First of all, let's examine the asymptotic behavior. What if rho goes to positive infinity? In that case, the 1 over rho squared term and the 1 over rho term can be neglected because they're going to be very, very small compared to 1/4. We end up with a very simple differential equation, whose general solution is given here. It contains two terms, a decaying exponential and a growing exponential. Now, this exponential, the growing one, will grow and become infinity as the radius grows and grows, so it diverges and probably will prevent the wave function from being normalized. Therefore, we're going to discard it. Now let's examine the behavior when rho approaches 0. In that case, the 1 over rho squared term is going to be the largest. 1/4 drops completely out, and this term is going to be intermediate. For very small rho, the second term here will dominate. The equation now looks like this, in this limit. The general solution for this again contains two terms, rho to the power of l plus 1 and rho to the power of the negative l. You can check this by inserting it into the equation. The first term clearly behaves well if rho gets really small, because it gets small as well. The second term, however, has a negative l as an exponent, and so if rho gets really small, this number becomes really large and prevents normalization of the function. So, although mathematically sensible, it is physically not meaningful. Let's drop it. Next step. Let's utilize this asymptotic behavior we found and write u now as a product of the first asymptotic term we found times the second asymptotic term we found times some function L that collects the remainder of the behavior and still needs to be determined. If we insert this expression for u in the previous differential equation, we'll get this equation here. It does not look very promising at this point, but it will be very easily solvable using a power series method. In that method, we expand L of rho as a polynomial that runs from 0 to infinity, a sum of CQ, which is a coefficient, times rho to the power of Q. Written out, it means there's a constant term, Z0, plus a linear term, Z0 times rho, plus a quadratic term, C2 times rho squared, plus and so on and so on. If you insert this expression into this differential equation and do a lot of tedious math, you will end up finally with a recursion relationship for these coefficients CQ in this polynomial. This recursion relationship is the following. CQ times an expression, fractional expression, equals the new CQ plus 1. So if you start with CQ0, using this equation, you can compute C1, and then using it again, you can compute C2, and so on up to infinity. So we have found the mathematical solutions. We have two free choices here. We can pick the C0 we want to start with, And also notice that this expression contains k. And if you remember, k was equal to the square root of minus 2me divided by h bar. The energy here is still unconstrained. We can pick it freely. So mathematically, E and C0 are free parameters. However, some of these choices might lead to functions that are not normalizable and not physical, and we have to discard it. So which one of these solutions are not normalizable? Well, any polynomial that has an infinite amount of coefficients in this example will diverge. So the thing we have to require is that the series C0, C1, C2 must terminate. In other words, there must be some maximal Q value for which the coefficients Qmax plus 1 above are 0. For example, if Qmax equals 5, it would mean that C6 and C7 and C8 and so on should all be 0. If you write this out using the previous equation, we get Qmax plus L plus 1 minus B over 2k has to be equal to 0. Now this clearly, since L is an integer, then we know that from the rigid rotor, and Q must be an integer since it's an exponent for the polynomial, this whole expression is an integer. Let's abbreviate it with n. And since we're adding n here at the plus 1 at the end, n is going to be larger or equal to 1. Rearranging this, we end up with n minus b over 2k equals 0. Since n is an integer, of course b over 2k also needs to be an integer. Now we can insert k and b and see what we get. First, let's rearrange it and write k squared equals b squared over 4n squared. Inserting the expression for k, and remember k was equal to the square root of minus 2me over h bar, we obtain this expression here. And now we have an explicit expression for the energy. Rearranging it, basically moving this stuff in front of the energy over to the other side, we get the final energy expression for the energy. The energy is quantized. It can only have specific values. Minus 1/4 of 2me over h bar squared times the square of ze squared over 4 pi epsilon 0 times 1 over n squared. We finally found the physically allowed energies. Only if E has one of these values will the wave function be normalized. Let's summarize. We found the energy eigenvalues, En. They can be written in this form, which we've seen on the previous slide, which after some simplification yields a more simple form that is shown here, where I've utilized A0. A0 is the Bohr radius, which is about 52.92 picometers. This expression also still contains the nuclear charge z squared and depends on this integer number n, which is a quantum number. If you plug in the values for these various fundamental constants, you end up with negative 13.6 eV times the nuclear charge squared divided by the quantum number n squared. We see that the energy is quantized, and any other energy would give non-physical wave functions. So, what are the values for these quantum numbers? If you choose an L, n has to be larger than that. Remember, n was equal to Qmax plus L plus 1. So even if Qmax is 0, n has to be at least 1 larger than L. So it could be the L plus 1 or L plus 2 and so on. Now we can turn this around and we can pick an n and ask ourselves, what values of L can we have? There, we can rearrange this and we can say L equals n minus 1 minus Qmax. Now Qmax is minimally 0, so in the best case we get an L equals n minus 1. If Qmax is larger than 0, then L is smaller. In the end, we'll end up with L that can have assumed values between 0 and n minus 1. So, in summary, we have three quantum numbers. We have n that can have values from 1, 2, 3, and so on. This is called the principal quantum number. L is the orbital angular momentum quantum number and can have values between 0 and n-1. And lastly, m sub L is the magnetic quantum number that can run from negative L to positive L. We had this quantum number already in the rigid rotor. Finally, note that the energies depend only on n, or n squared, and do not depend on L or m. So clearly we'll have many states with different L's and different m's, but identical n that all have the same energy. They're degenerate.